Okay, let's look real quick at electric potential surfaces. All right, now we're assuming a uniform electric field in here. So the amount of energy it takes to move this, say, to go from here to here, if we were a charged particle, is zero. Because it's just like how much did the energy change from here to here? Because the potential difference lines are running parallel to the plates here, but perpendicular to the E field. Okay? It is one in which the electric potential does not vary. It takes no work to move a charge along an exponential surface. Okay, notice we've got these different exponential surfaces, this VB to VA. Now the potential changes. If I go from VB to VA, that'll take work, or I'll lose potential energy. In other words, the electric field might do work. If it was a positive charge going from VB to VA, that's the way a positive charge would want to go. So the electric field does positive work. If I'm a positive charge and I'm trying to go from VA to VB, I'm positive that will take external work from some other force. Some external force will have to push me up, and the electric field will actually be doing negative work opposing it. Just like when I pick something up, gravity does negative work, but I'd have to do positive. So positive charge goes from VB to VA and loses electric potential, gains kinetic energy. If a positive charge goes from VA to VB, it gains electric potential energy. And it took work to do it. All right, electric potential are analogous to contour lines on a map. Here's my positive charge, this is V4. See, look, V4 gets bigger and bigger and bigger and bigger as I get closer and closer to this charge. The voltage gets higher and higher and higher. Like, are always perpendicular to electric field lines. Kind of remember that. That's a little thing that I like to throw on the conceptual part of your exam. Look, now I've got an electric field. I've got probably right here, V2 is equal to 0. But the electric field's not equal to 0. But the voltage is equal to 0. But right here it's positive, and down here it's probably negative as it's starting to bend around this negative charge here. So V1 is greater than V2 is greater than V3. All right, the direction of the electric field is that in which the electric potential decreases the most rapidly. Okay. So in other words, the electric field doesn't go like this because the potential doesn't decrease that rapidly. But if it goes from here to here, that's the direction. See, the direction of the electric field is straight. So therefore, the magnitude of the electric field is given to the change in potential. Like the change in potential went from here to here, divided by the distance that it traveled. Okay. All right. It won't go this way. It'll go this way. Follows change most rapidly. Okay, approximate voltages. Household batteries, cloud to earth, 100 megavolts or more. Across nerve membranes, 100 millivolts. That's why just a little bitty shock, 100 millivolts, that's 0.1 volts. 0.5 volts will kill you. Or, well, 0.5 amps will kill you. So a little 0.5 volts, because you actually create like 10,000 volts when you walk across a floor. Or automotive ignitions of plug firings, 10,000 volts. Hopefully it doesn't have that much amperage, which we'll learn about in chapter 17. Okay, I think we're done. I think these are the big points, and you can also, heaven forbid, read the book between 16.2, read about 16.2, and then so we're going to focus on this tomorrow in class. And what I'd like for you to do, what I have done, it's open to most recent September 1 in-class problems. I've given you a place to put your quizzes, and I'm going to put these problems here. I'm going to put these problems on Blackboard so that you can bring them to class. Okay. And I'll put that in the message when I say I'm done here. Okay? That's enough for the video today.